things last. You realize the sun don't go down. Just illusion caused by the world spinning round. I love me some Flamin' Lips. Do you realize? All right, folks, let's get it going. Here we go. Okay, let me start a stopwatch. All right, so picking up lecture number 2 on rotations. So let's look through these learning goals. I just got these posted up. So know the right-hand rule and be familiar with the equations from classical mechanics that govern rotational motion. So that's what we went over in the lecture 1. Be familiar, or that was lecture number 13. Be familiar with in-phase and out-of-phase rotations and how classical rotation becomes quantized. So be familiar with that concept. Be familiar with the magnetic quantum number, ML. Know how to solve Schrodinger equation for particle on a ring. And this last bit, be familiar with angle and angular momentum being complementary observables. I kind of left off right there, and we're going to be really hitting this in a lot more detail in the next couple of lectures. So I'll leave it at that, and let's get in to these slides, okay? So this is where we left off, right? We got that this is our wave function for the two-dimensional particle on a ring. Remember, two-dimensional because it's rotating in and out of the xy plane, where the angular momentum is pointing up on the z-axis, okay? And what happens when we look at the square modulus becomes independent of phi. And so what that means is the probability density is indefinite. We have a large degree of uncertainty in this, okay? And so what that means is angular momentum, Jz, and angle, phi, become a set of complementary observables. We're going to explore this, like I said, in much more detail in this talk and this lecture, as well as the next lecture, okay? So what we need to do, we need to come up with a new operator for angular momentum. And we're going to borrow more stuff from classical mechanics, okay? So the orbital angular momentum, so that can be described with classical mechanics, all right, given by Lz, which is x times py, momentum in y, minus y times px. So this is a classical mechanics equation. We also know from quantum mechanics, whoa, I don't know why my alarm just went off. It scared me though. Anyways, I'm gonna keep going. I'm gonna keep recording. So the linear momentum operator, we know from quantum, is this, okay? So when we're gonna combine these two things, right? Because we have momentum here and we have x. And so when we combine these two things, we get this two-dimensional, I'll say two-dimensional Cartesian, I think you spell that with 2 S's. So this is our two-dimensional Cartesian coordinate scheme with x's and y's. However, if you recall, because in this case we only have constant radius and we're not dealing with the theta dimension, at least not yet, our orbital angular momentum operator just simplifies to h bar over I times dd phi. Okay, it becomes very simple. Don't confuse that with the kinetic energy operator for rotations, right? Let's just back up and look at that one hot second. The kinetic energy operator, remember, was negative h bar squared over 2I times d squared d phi squared, okay? Our angular momentum operator is going to be h bar over I times d phi, all right? And so what is the big deal about this thing? Well, for one, we need to check that this is going to be an acceptable operator, okay? And so I've already given you the results here. So when Lz operates on psi ml, right, where here's my psi ml, then our result is actually ml h bar times psi ml, okay, right? So we get the eigen value, which is mlh bar, and we return back the eigenfunction psi ml. And so I'll just remind you really quick to do this operation of Lz on psi ml, right? So it's just simply h bar over I and the derivative in phi of this equation psi ml, okay? And so when we do that result, we get back ml h bar times psi ml. So I'll write that, it's ml h bar, and then that becomes divided by 2 pi e to the I ml phi, right? So that e I ml phi divided by root 2 pi is psi of ml. So this is fantastic. So we're working in the right direction with this orbital angular momentum operator. We recognize it's a valid operator because it gives us an eigenvalue. So we're going to use this angular momentum operator to continue exploring this uncertainty principle given by angular momentum and angle. But before we continue with that, I want to expand this particle on a ring model into a particle on a sphere. We're going to add in that third and final dimension, and that's going to really help us continue to explore the uncertainty principle associated with this stuff, okay? So I'll remind you, our particle on a ring was rotating perfectly in and out of the xy plane with angular momentum pointing in the z direction. If we want to expand this to become a three-dimensional model, it really becomes a particle on a sphere. And now what that means is my rotation axis now is free to pitch in and out of either the zy plane, right? I can keep rotating it like this, or it can pitch into the zx plane, right? Like this. And so the result of that, you can see this sphere that we have, is now we have to consider the angle theta that describes how this rotation plane pitches either in either the the zy or the zx dimension, okay? So here's what we need to do. Cry, pray, guess, solve, right? You are on top of that, okay? So maybe you're crying and praying right now. We're gonna guess and solve soon. And the reason why you might be crying and praying now is because this math gets kind of nasty. So here we have del squared, but in 3 dimensions, right? So we're still dealing with zero potential energy. We're still dealing with our translational kinetic energy operator, but now we've added that z dimension, okay? So through standard manipulation, I'll just say standard, this del squared in spherical coordinates becomes the following, right? All of our second derivatives in R, okay? Make sure that I'm on the right track here. Yep. And now what we have, this new complication, is the appearance of this seemingly innocent little guy called the Legendrin. And the Legendrin is not our friend. This is the equation. 1 over sine squared theta, second derivative in phi, plus 1 over sine theta, first derivative in phi, times sine of theta, first derivative in theta. So this is going to get nasty. So is there any simplifications that we can make? Well, yes. We remember that we have a constant radius, right? So that means all of these terms involving derivatives can go away. And now what we get is our del squared is going to be 1 over r squared times the Legendrin squared. And so now our kinetic energy operator becomes negative h bar squared divided by 2m r squared that comes from right there, okay, times the Legendrin squared, and that all becomes negative h bar squared divided by 2I times the Legendrin, okay? And so this seems fairly innocent, right? When I put together, you know, here is my Schrodinger equation. It doesn't look so terrible, but remember, this Legendrin, right, is intense, okay? So we're gonna have to deal with it. So finish crying and praying about the Legendrin, and let me find my right page in my notes here, and then we're gonna do it. Aha, okay. So let's solve this thing. So we're gonna take advantage of using separation of variables, because you might have noticed here we have psi as a function of theta and phi. So in my separation of variables, I've got my theta component right here. So I'm going to say, you know, a function theta. I just used a capital theta and a lowercase theta. And then our function phi, a capital phi and a lowercase phi. Okay, so those are our separation of variables. So what we know is that our Schrodinger equation is given right here with just our kinetic energy operator. And we've also got our Legendrin. So now, putting this together, okay, I'm going to go ahead and first put my Schrodinger equation in a form that I can use. So the first thing that I'm going to do is the following here. I'm going to say, I'm going to write up here, I'll write Legendrin squared psi of theta phi equals negative 2IE divided by h bar squared times psi of theta and phi. And so now, right, so I just moved all the constants over. And now what I'm going to do is apply the separation of variables, and I'm also going to plug in all of these terms for the Legendrin. Okay, so that's going to go as the following. I'm going to start way over here and hope that I left myself enough room. Okay, so I'm going to start with that 1 over sine squared term. 1 over sine squared of theta. And now partial derivative of phi. Okay, so I'm going to write the partial squared of theta and phi of phi. And this is only the partial derivative in phi. Okay, right? So psi is theta, phi, phi. Okay, so now my next term is this plus 1 over sine of theta. And then now I've got a first derivative in theta. Okay, so let's see where that all went. Oh, and what I'm also going to do to make this, oh yeah, I'm just going to write it as such. Okay, so partial of theta, I'll just make sure I stay consistent here. Okay, we'll use little serifs to note that that's capital phi. Okay, partial in theta. And then now that's times a sine theta. And then once again, another derivative. Okay, so I'm looking at my notes here and I'm trying to figure out what I did differently, because I've got two derivatives written there. Why did I do that? Okay, well, we're just going to go for it. We're just going to write it, and we're going to see what happens. Phi, partial theta, and all of this, so equals negative 2IE divided by h bar squared times, of course, my wave functions that have now been separated. Okay, so what I'm going to do now is pull out all of the functions that don't have dependencies. So for example, here is derivative in phi, so I don't need to worry about the theta when I'm taking the derivative in phi. So I'm going to write that out here, okay, divided by sine squared of theta. And then now I've got my partial derivative in phi of just phi. Okay, great. And then now I can do the same thing here for this derivative. Okay, and what I'm going to do here is collect like terms. So I'm going to factor out that derivative. You'll see here in a second. I'm just going to write it all out and then I'll describe what happened. Okay, so sine theta, and then now this is just partial of theta, and then yes, very good, my theta function. Okay. So I know why I'm confusing myself, because this term here only applies to the sine of theta. So that is why I confused myself earlier. So that means I don't need to have this in here. I knew I was confusing myself somehow. Okay. Right, so this is just, order of operation, right? Partial of phi operates on sine of theta, okay? So that means that I have up here phi divided by sine of theta, partial of theta, okay? And then now I need a sine, yes, okay. Right, the partial of theta of sine of theta. Okay, brilliant. And then now what I can write out here, so I've only needed to factor out this phi right here. And so now that's going to become partial of theta times theta. And of course, all of that still equals this. I'm not going to rewrite that part of the equation. This all still equals this side. And now what I can do is divide and conquer. So I'm going to divide both sides by this wave function theta theta phi phi. Okay? So when I do that, when I divide this out, okay, check this out. The theta term is going to cancel. All right? But I'm still going to end up with a 1 over phi. Let's rewrite that again here, okay? So, and excuse me, so let's write that as, I'm going to end up with a 1 over sine squared of theta times. And so now I'm dividing this whole term by theta phi, so the theta cancels, and now I just have 1 over phi, okay? And then I still have my derivative in phi. I can't cancel that out. Okay. And then now I can say plus, all right? And so now I'm going to have a 1 over sine theta. And my phi cancels, so I'm going to also have a 1 over theta function. Okay, and then now I'm going to have a partial of theta. It blanked out on me. This is going to be interesting on the recording. In any event, so now I've got the partial of theta sine theta, okay? And then now I have, yes, brilliant. I still have my function right here, partial of theta, okay? And then now what I did, I'm going to add this part over so we can set all of this equal to 0. And of course, the theta and the phi have canceled. And so that all equals 0. And then now, I think I left myself another page. Oh, good, a whole another blank page. And so now I'm going to clean up some of this algebra by collecting some of these 1 over sines. Okay, so I'm going to multiply everything through by sine squared of theta. All right, so when I do that, I get the following: 1 over phi of phi, and then my second derivative in phi. And then I get a plus sine theta over the function theta times derivative theta of sine of theta times the derivative in the big function theta with respect to theta, and then plus 2ie over h bar squared times sine squared of theta equals 0. Oh my goodness. Okay, so now we are finally in a position where we can separate. And we're going to separate the phi's and the thetas. I promise you this is going somewhere logical. So when I separate the thetas, I get 1 over. Oops, that's supposed to be a theta. Okay. So I get that, and then of course this second derivative of that function phi. And so all of these terms correspond to the sine, okay? And I can even separate out that sine of theta because this function doesn't have any of those dependencies, and I can separate them back out because I'm going to multiply them back together, okay? So then that becomes plus 2ie over h bar squared all equals 0. And I'll remind you, we've already solved this thing, okay? So look, I've got that phi function right there. I'm going to keep this going with the algebra, and I'm going to rewrite this as the following. So I'm multiplying through this phi over here, right? And so now this becomes second derivative of this function phi plus 2ie over h bar squared times phi equals 0. We've already solved this. We have already solved this function. I'll show you. It's back in the particle on the ring model. Look, there it is. I think I just passed it. Yes, look at this, right? Second derivative of phi of some function psi plus 2ie over h bar squared times psi equals 0. Okay, we've already done that. Brilliant. So we have a solution for this already. That's fantastic. We know that, of course, ml equals the square root of all of those constants, 2ie over h bar squared. We also know that this wave function, which we're now calling phi, right, will equal e to the I ml phi, where that ml takes on the plus minus values. And of course, this has to be normalized, and we normalized it already. Fantastic. So when we go to separate the phi dimensions, I'll just write all of that out. Sine of theta over the function theta times dd theta of sine of theta times dd theta of the function theta plus, and so I'm going to write all of this, this 2ie, that's still there, because we have to keep it attached to the sine squared, okay? And then also what happens is, oh my gosh, I'm failing at what I did here. Well, I'll write down what I have in my notes. I've got a 2ie over h bar squared times sine squared of theta equals all of these constants, 2ie over h bar squared, all squared. And why did I do all that? I think I did that to factor out that sine squared of theta from this phi. But it doesn't matter. And the reason why it doesn't matter is because our guess for this theta function is really difficult. We're not going to do it. So solving this equation becomes well out of the scope of the class. I've already been flubbing around with this math for the last 10 minutes. I would have to flub around with this math for a couple of more days, or have you take partial differential equations. So we're not going to do it. We're not going to worry about solving it. But the important thing to note is our phi still has this e to the IML phi dependence, okay? And so when we go to guess for theta, and then we plug our guess solutions back into this equation, right? When we recombine those results, so we put this EIML phi back into here, and whatever crazy guess we've come up with theta, we put back into here, we get a very special result, okay? And that special result is what we call the spherical harmonics, all right? So in other words, this theta of theta times phi of phi equals my original wave function, okay? And then when I go to normalize that wave function, so this is why I didn't normalize this phi result, because we have to normalize these two results together. So when you go to normalize this wave function with theta and phi dependencies, we get a very special function called the YLMLs, which we call the spherical harmonics. And what's special about these spherical harmonics is we get a new quantum number L that arises from trying to solve this system of equations. So I'm not going to hold you responsible for continuing through this solution. So we got a pretty good way through it, applying the separation of variables trick. But effectively what we get, the normalized wave function of theta and phi, becomes this YLML function, okay? And a new quantum number arises from the boundary conditions. We call it the angular quantum number L, which should be familiar to you. And that takes on values 0, 1, 2, etc. What also becomes really cool in this solution is trying to solve these things together, right? Because we have the ML term right here, which comes from the phi solution. We get the L from the theta solution. However, what becomes difficult is the L and the ML have to be connected to each other. And it becomes the following. So ML takes on two L plus 1 values. That is L, L minus 1, all the way down to minus L. So where do I get this 2L plus 1 values? Well, for example, if L is equal to 1, then ML can be 1, 0, or negative 1, right? So where do I get the 2L plus 1 values? Well, remember, if L was 1, 2 times 1 plus 1 equals 3. That was 3 values of ML. So we're going to see this 2L plus 1 come up, okay? So what else do we get from solving the spherical harmonic particle on a sphere? Well, we get the energy solution, and we actually get the energy solution in terms of quantum number L, which is cool. It becomes L times L plus 1 times h bar over 2i. So this h bar over 2i should be familiar, because recall when we did the particle on a ring, let me find that solution for energy. Yes, look, when we did particle on a ring, we still got that h bar squared divided by 2i, however it was times ml squared. So we're really seeing the connection between ml and L from solving this model. At least you'll have to take my word on it, because I'm not making you finish doing this solution. Okay, a couple other things to point out before I wrap up this lecture. These spherical harmonics, much like the Hermite polynomials, really start to blow up when you add in their quantum number dependence. So for example, when you have L equal to 0, and then of course ML, the only value you can take is 0, because, right, 2 times 0 plus 1 is just 1. So when L is equal to 0, ML has to be equal to 0. Well, my YLML, my spherical harmonic function, becomes the square root of 1 over 4 pi. Okay? With no theta or phi dependence, which is kind of cool. We'll see the manifestation of that in a moment. When L is equal to 1, then ML can be 0, plus 1, or minus 1. And now what we should notice is the plus 1, minus 1 states have the same function, although they're just different in sign. So for example, when ML is plus 1, so the notation of this is kind of weird. So when ML is plus 1, the function starts as negative square root of 3 over a pi sine of theta e to the positive I phi. When ML is equal to negative 1, the function becomes positive square root of 3 over a pi sine of theta e to the negative I phi. Okay, so keep that in mind when you're noting these functions. And you'll notice definitely as we get to bigger L and ML values, the spherical harmonic functions become a lot more complicated. So it would have taken us days and days and days to solve this thing, okay? So that's why we're not going to do it. But carrying along, okay? The normalized particle on a sphere Schrodinger equation becomes the spherical harmonic functions. The spherical harmonic functions give rise to new quantum number dependencies, that is L, angular momentum, or angular quantum number, and ML, magnetic quantum number, and we can see the dependence of them. And then now what we also see is some other unusual integral properties that I don't think are as important but worthwhile to note. And I'm not going to review those in great detail, but here we can see the spherical harmonics are orthogonal and normalized in the following sense. Okay, so so this is the normalized equation, and this is the orthogonal equation. And this is kind of a weird orthogonal equation because you notice here that it's using 3 spherical harmonic functions, and that's to set up what we call the vector model, and I'm going to be going that in the 3rd lecture of this material. So I'm not as concerned with you knowing these integral properties, but I just wanted to present them, that the spherical harmonics do have these integral properties, okay? Another thing that we can start to look at is when we plot these spherical harmonic equations, which we're going to do. You're going to do that in your Math 6 assignment. They start to take on some familiar shapes. So let's look back to this L equals 0 and ML equals 0. Okay? So in the solution for the YML, there's no theta or phi dependence. And so what that means is the y00, so I would call this solution here the y00, because L is 0 and ML is 0. Look, it's just a sphere, like an s orbital, right? Awesome, cool, because it is an s orbital, but you don't know that yet. We don't know that yet. We'll get there. So what about these functions? Well, right here, so this is also really cool. So this one is the y10, and I want you to stare at that thing for a minute and think about what that looks like. If you're saying a p orbital, then you are exactly correct. And in fact, it is specifically a pz orbital. And this is going to come full circle with our Heisenberg uncertainty principle, why that one is pz. So now what's going on with this donut looking shape? So this one is the y1 plus or minus 1. So because the plus, so remember, I talked about those ML states, they're doubly degenerate, okay? So why does it look like a donut? Well, now what I want you to imagine, take this p orbital, okay? Rotate it 90 degrees, and then now take that same p orbital shape and smear it all the way around your xy plane. And that's the shape that you would have. And so the reason why that doesn't resolve perfectly into a px and a py is because, as we shall see, there is an uncertainty relationship associated with those x and y dimensions. We see the same thing with L is equal to 2. So the y2, 0 is right there, and it is a perfect dz squared orbital. That's what we call that thing. So then now the y2 plus minus 1 and the y2 plus minus 2, they kind of look like d orbitals, but not quite, because we have to deal with Heisenberg. And then now similarly also the y3, 0 looks exactly like an FZ orbital. The other orbitals don't quite look like what they're supposed to look like because we haven't dealt with Heisenberg yet. All right. And plus, we also haven't dealt with what happens when we change the radius. So what we have in these pictures right here, these regions are showing you the angular nodes. So we've talked about nodes in the translational model. And as it turns out, we can call those radial nodes because those nodes appeared on the radius axis. And we'll hit those again soon. Okay. The angular nodes are a little bit more hard, or they're a little bit more difficult to visualize. So these angular nodes are represented by shaded regions given right here. So the L00 doesn't have any angular nodes. The L10 has angular nodes, and to be determined how many there are. But I just wanted to start pointing out that we can start to kind of get a sense of what's happening, foreshadowing, talking about our atomic orbitals to come. Okay, and so let's see here. So that's a good place to stop. And in the last video of this content, I hope it'll be the last video of this content, we'll continue on with this model and build up what we call space quantization and the vector model. Okay, so in this lecture, what I went through was be familiar with angle and angular momentum being complementary observables. So I just kind of told you that they are complementary observables. In the next lecture, we're going to go again into more detail on that. So be familiar with the angular momentum operator. So that's how we started the lecture, talking about the angular momentum operator, which has eigenvalues MLH bar. So know how to solve Schrodinger equation for particle on a sphere and be familiar with its solution for energy in the wave function. So I really should have said be familiar with solving the Schrodinger equation, because we kind of got about halfway through it and then just cut it off because it's more complicated than is worth our time in this class. So be familiar with angular quantum number, okay? And then be familiar with the spherical harmonics. And so the last thing in the lecture, which will take quite a bit to go through, but the last lecture, lecture number 15, I believe, we'll talk about the vector model, okay? I'll see you in the next video, folks.